In the last lesson, I covered the concept of FPGAs, we learned about the concept of HDLs, and then next we installed all the software that we need. Using that software, we were able to create an application that was able to blink the LEDs on and off for 1 second. Now in this lesson, what we're going to do is I'm going to go over a top-level design that consists of several VHDL components and how to interconnect those. We're going to use the inputs and the outputs on the Mercury board. I'm also going to go over how to handle button inputs, finite state machines, and registers. And I'm going to go over all these concepts by going over a simple example. In this example, what we will be doing is taking a button input and counting the amount of times that the button is pressed. And that count is going to be displayed in binary on the external LEDs. Now I just described kind of what the goal of the project is going to be. And the goal is to take in an external button input and process it in such a way that we're going to develop a sort of counting device that is going to interface to external LEDs to count how many times the button was pressed in binary. So right now I'm just going to add the external peripherals for that. So here are the peripherals. We have the button input, and you can see that there's a pull-up resistor that takes this node high. And then whenever the button is pressed, it will bring this node low because it's connected to the ground. And then over here is an array of 4 LEDs that's going to be connected externally from the Mercury board. Now, whenever I want to develop a VHDL application, no matter how big or small, it's always a good idea to draw a sort of map of how this is going to look like beforehand. You don't really need to know exactly how the components that you define here are going to work exactly. You just kind of want like an idea of what you're going to do, like how your machine is going to work. So this is kind of a bit of a top-down approach where I'm going to define several modules that I'm not really too sure how they're going to work yet, but I'm just going to kind of declare what they're going to do and what I'm going to expect them to do. So I'm just going to get started. We first know that we want some sort of module that's going to take in this button input, and then every time it sees a rising edge, it's going to increment its counter and display that count on the LEDs in a binary count system. So I'm going to add that module now. So this is the module that I'm proposing to do that. What I want this module to do is it's going to take in this button input, and then this counter out, you can see that's a thicker arrow because it's an array of signals. This array of signals consists of 4 lines that's going to connect to each one of these 4 LEDs. And then this button gets inputted here. I have a clock input and a reset input as well, which I'm going to use this onboard button to act as the reset. And then the onboard clock I'm going to use to drive the clock input on this module. But right now I'm already seeing a problem with this design, because this would work really well with the button if this button was an ideal button where the signal looked something like this, where, well, we know it by default it starts off high, and then once the button is pressed it goes immediately low and stays that way. But we know that that's not going to happen, because since this is a mechanical switch, what's really going to happen is that there's going to just be a ton of noise where you just get a bunch of jittery spikes in the switch before it finally drops down low. And you don't want your module here to inaccurately count each one of the spikes that occur. So it's pretty obvious that we need to precede this button input with another module. This module is going to clean up the signal here, and it's going to take something like this and turn it into a clean input. So now I added that new module and I called it the debounce hardware. I made this input called raw in, which is going to take in the raw button input. And then it has this clean out output that's going to connect to the clean button. And just as the button is connected to reset on board and the clock is driving the clock input of the FSM counter, the same thing is going to happen for this module. The button's going to connect to reset and the clock's going to drive the clock input. But things aren't exactly the way I want them yet. I could hypothetically connect this output straight to these LEDs. But one thing that I like to do is whenever I have an array of outputs like this, what I like to do is I like to precede that with a register. And what the register is going to do is it's going to take values from the counter and then drive those outputs for me. It's going to be kind of the driver for these LEDs. So I'm going to eliminate this connection here and add the register here. So here's my register that I added. Now hopefully you know how a register works, but I'm going to try to do my best to explain it. What I'm going to do in this case is I'm going to have a 4-bit register that connects directly to these LEDs and have the counting output connect to the count of this register. A good way to look at a register is kind of a device to save information. So say for instance, we have a current count of 3 and then we go to 4. And you want to display 4 on the LEDs, so that's going to look like this. So this signal was previously equal to 3 and then readjusted it to 4, but 4 doesn't automatically get passed to the output here to display on the LEDs until you set this load signal high. And once you set it high, then 4 gets passed through to the output. But after you have 4 passed through to the output, you don't have to worry about keeping load high anymore. You could change this, you could have this be equal to 4 and change this input as much as you want, but until you load the register with this signal, then none of the inputs here are going to get passed through to the output, and 4 is going to remain there. And as you can see, the register also has clock and reset input. So this is kind of what I mean by a map of how our system is going to work. It makes developing the VHDL for your application way easier because now you can kind of see what it is that you're developing. Also, I added this load register signal to connect to the register. So this is kind of how everything's going to look. And now we just have to implement this in VHDL. But before we get into the VHDL, I kind of want to think about how we're going to do this debounce hardware. So let's consider how we're going to do this debounce hardware. For the input to the debounce hardware, we have a button that goes to the raw in, which is our input. And when the button is pressed, it's going to go from high to low. But for every single clock cycle, since this is not an ideal button, it's first going to just kind of start off high, and then for the rest of the clock cycles, when the button is pressed, it's going to just kind of jitter a little bit until it finally settles and just stays low. So what we want to do is, for this debounce hardware, is we're going to use the debounce hardware to detect a time when we have a consecutive period of 1s and 0s to kind of test for the stability of the button. So if we have a signal, for instance, which is 8 bits long, we'll call this signal S debounce. So if S debounce is 8 bits long, then it would look something like this. So kind of my plan for the debounce hardware is that on every clock cycle, on every rising edge of the clock, basically what we're going to do is we're going to take the signal S debounce and assign it 6 down to 0 and concatenate that with our raw in up here. So how is this going to work? Well, let's say for instance that the button is currently high, which means S debounce would be equal to all 1s. But if the button becomes pressed and then we start getting this sort of jittery feed that goes in, then on the next clock cycle, S debounce is going to equal 1, something like this. And then on the next clock cycle after that, it might look like this. And why does it look like that? Well, on every rising edge of the clock, we are taking the bit 6 down to 0, because remember this is an 8-bit long signal, and so we're going to take the least significant 7 bits of S debounce, shifting them down to the left over here. So that's where these ones went to. They just shifted in here, and then we concatenated the end of S debounce with whatever our raw input is. And for us, it was 0, so then 0 got shifted in. And then on the next clock cycle, these 7 bits shifted over to here, and then the 1 got shifted in to SD bounce. So this is kind of our way to detect whether or not the button is stable or not. Because if the button is stable, and if it's a stable high, then it's going to be all 1s. But if it's a stable low, then it's going to be all 0s. So what the logic is going to kind of look like is if SD bounce is equal to all 1s, then our clean output, which is the output of our debounce hardware, is going to get assigned 1. And then else if SD bounce is equal to all 0s, then clean out will get assigned 0. And then else, so if SD bounce is kind of a mixture of 1s and 0s, we're just going to keep clean out whatever it was before. We're just going to keep it the same. So if it was high at first, but then some 0s got mixed into it, then it's just going to stay high, and it's not going to switch to low until it's all 0s. But there's kind of a problem with this hardware right now, because our clock input is 50 megahertz, and SD bounce is 8 bits long. So what's going to happen is that this SD bounce is really only verifying for 8 times the period of 50 megahertz, which the period of this is 20 nanoseconds. So that means SD bounce is only verifying 160 nanoseconds. But that's kind of a problem because for a proper debounce, a button doesn't really stabilize for about 10 milliseconds, which let's roughly approximate that to 100 hertz. So if we take a calculator and say 50 megahertz, which is 50 million, divided by 100 hertz, which is here, for the length of time that we need to verify our button, we're going to get 500,000. 500,000 clock cycles is what we need to successfully verify a button press. And we only have 8 bits, not 500,000. So this is kind of introducing a problem because this isn't really going to work because 160 nanoseconds isn't long enough to determine whether or not the button has become stable or not. Now we could make our signal 500,000 bits long, but that's a bit messy and that's kind of a hackish way to do it. But what's a cleaner way to do that is change our clock input. If we change our clock input to be something that is significantly slower, instead of being 50 megahertz, maybe we make it into a couple hundred hertz or something, then 8 bits would be long enough so that way we could reach our 10 millisecond goal to smooth out the button. So let's go back to the flowchart and add that. And as we were talking about before, the 50 megahertz that is getting fed into this debounce hardware is just way too fast in order to accurately verify whether or not this button is stabilized or not. So what we're going to have to do is we're going to have to build another tiny module that takes in the clock input here, and then it outputs a significantly slower clock signal out of it, which is going to get fed back into this debounce hardware. And that clock is going to be slow enough to the point where the SD bounce signal inside of this hardware will be able to verify for at least around 10 milliseconds to verify whether or not this button has been stabilized or not, either stabilized high or low. I'm just going to add that module now. So this is the new module that I added. I called it clock div 65536, which means it's going to slow down this 50 megahertz clock signal 65,536 times. So it's going to be that many times slower. And that probably kind of sounds like an arbitrary number to pick, but there's a specific reason that I chose that one. So for clock dividers, what I usually like to do is I like to pick a number that is a power of 2. And there's kind of a good reason to use a power of 2 to act as your clock divider, but I'll show that when we implement it in VHDL. If we use this calculator, you can see that 2 to the power of 16 is 65,536. And if we divide 50 million by 65,536, then we get hertz of 762. And the period of 762 is like 1.3 milliseconds. And then times that by 8 bits because we're using 8 clock cycles in our debounce hardware to verify the button press. So the period of the slow clock that's getting input in here times 8 is going to be 10.4 milliseconds. So just with this simple math, we can see that this clock division here will slow down this debounce hardware enough so that way we can successfully verify any button presses that are made here. So I'm just going to connect that now. And then obviously these resets will get attached to this button here. The reason why I'm not putting debounce hardware on this button is because I don't really care if these modules get reset multiple times accidentally. Whereas here I care about how many times the button is pressed. That's kind of something that I care about. Whereas here, if it resets multiple times, it's not going to affect the system from the user's perspective at least. So this is everything we need, and now that we have everything mapped out that we want, we should just get going and program all this in VHDL. So here I just opened up ISC Design Suite, and I started a new project. And for this project, I'm going to name it Binary Counter. And this is just where you set your parameters for your FPGA again. I covered all this in the previous video. These settings for me are correct for the Mercury board. So we have 4 pieces to design, and of these 4, I think I'm just going to start with the register. Right click on the FPGA, select New Source. VHDL module, I'm going to name it Reg LEDs. Now again, here is where you select the inputs and the outputs for this register. Now in our map, we have these 4 inputs: reset clock, counter in, and load register in. And then the single display LEDs output that's going to just be driving the LEDs here. That's just what we're going to define there. I have clock, reset, counter, display LEDs. And this input is 4 bits long, 3 down to 0, and the output, since it's driving 4 LEDs, is 3 down to 0. And Xilinx generated the skeleton code for us, so we're just going to enter in the logic that we want as we did before. I'm going to start by creating a process that gets triggered by clock and reset. And there we're just going to tell Xilinx to begin the process there. And process. And before I get writing in the process, what I like to do is declare signals that's going to eventually just get written to display LEDs here. So I'm going to declare that signal now, where the X here means hex, hex 0. In hex, 0 is 4 bits long, so that's just 4 bits of 0. And on this module, I'm going to have an asynchronous reset. I'm going to create an if statement if the reset goes high. And I forgot to assign S display LEDs back to the output, so I'm just going to do that here. Next, I'm going to add the else if statement for the rising clock edge. Else if clock tick event and clock is equal to 1, then as we covered in the last video, this is if on the rising clock edge. So if a rising clock edge occurs, if load reg in is equal to 1, then S display LEDs now gets assigned whatever is on the input counter in, and end that if statement and end this if statement. And that's That's all there is to make a simple register like this. And yeah, registers are pretty easy. So hopefully that one will be all good, and I'm just going to make another one. This time I'm going to make the clock divider. Clock div 65536. And if you remember, we have one input clock, which is going to take in directly the clock source, and then it's going to output the slow clock. In clock slow for out. Finish. I mentioned before that I like to have my clock divider be a power of 2, and 65,536 is 2 to the 16 power. Oops. It's 2 to the 16 power. So what we're going to do is we're going to define a signal, which I'm going to call the clock counter, which is a standard logic vector 15 down to 0. So it's 16 bits long, and it's going to get assigned X. So it's just going to start off at all zeros, and I'm going to define another signal that is going to get assigned to the output clock slow. So process, in the sensitivity list I add clock and process, and then I'm just going to assign my signal back to clock slow out here. So I'm just going to burn through the logic really fast and explain it after the fact. So if on the rising clock edge, then as clock counter, our counting variable will get incremented once. And I'm going to take s clock slow and give it the most significant bit from clock counter and if. And that's all you need for a clock divider, and that's kind of why I like using a power of 2, is because the logic is just as simple. And if you don't understand what I did already, is, well, this clock counter is 16 bits long, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you know that when on every single clock edge you can see I'm counting, so what's going to happen is it's just going to, clock counter is going to start looking like this. And you can see clock slow is just getting this last bit. So whatever this most significant bit is going to be written to here. And that is going to be 65,536 times slower than the actual clock. And maybe kind of simplify it to make it easier. Let's say clock counter is just 1 bit long. So it's just starts off as 0, then it goes to 1, then it goes to 0, then it goes to 1. Now, you're assigning clock slow, you would just assign it just at 1 bit. So let's say your clock is like this. And on every single rising clock edge, you increment the clock counter, which in this case we're saying is just 1 bit long, just for sake of understanding. So it starts off as 0, and then on the rising edge of this clock, it'll go high. But then it won't count again until it reaches the next clock cycle. So it's just going to stay high until it reaches this clock cycle, then it's going to go down low, then stay there until the next rising edge of the clock. And it's just going to look like that. So you can see that if you were to assign clock slow this red signal, you can see that it's that clock slow, that's ugly, is half the clock. Okay, well, it's half the clock. Because for every 2 periods of this clock, you get 1 period of the slow clock. And as you start increasing the bits here in clock counter, and when you assign clock slow the most significant bit, you're dividing the speed that clock slow runs at by a power of 2. So when you have 16 bits and you assign clock slow the most significant bit, then you're dividing it by 2 to the power 16, which is where 65,536 comes from. So just clean all this up. Oh, And there's one more thing is since I'm using a type of arithmetic here, it's going to complain because as these libraries stand right here, it's not going to support this arithmetic. Now, what a lot of people like to do is that they like to use this numeric library, which is the general sentiment for that seems to be that this is the correct one to use, but for some reason that one never works for me. For me, I just personally use the IEEE standard logic unsigned, and this library will allow you to use the arithmetic here. And just with that, you're already done with the clock division. Yeah, the next guy I'm going to make is the debounce hardware, which has the raw in, clock, and reset inputs, and the clean out output. So, new source again, VHDL file, and debounce hardware. Raw in, clock, reset, and clean out. And first thing I do is define a signal to get written the clean out. And as we were talking about before, we also wanted to declare a signal S debounce, which is going to be 8 bits long, and that's going to test the stability of our button. And add the process clock with the asynchronous reset, begin process, end process, and assign clean out the signal S clean out. Now if the reset goes high, then S clean out gets assigned 0, and S debounce goes to byte 0. Else if on the rising edge of the clock tick event, and clock is equal to 1. So on every rising edge of the clock, this is what we're going to do. We're going to assign S debounce, like we were talking about before, we're going to shift it in. So S debounce is going to get assigned the least significant 7 bits of itself and concatenate those 7 bits with whatever is on the raw input. Now if S debounce is equal to all ones, or if it's FF, then that means our button is a stable high, which means S clean out we should assign to be high. Else if S debounce is all zeros, or it's byte value 0, then we can say that the button is a stable low, so clean out will be 0. And we said that if it's not all ones or all zeros, if it's a mixture of ones and zeros, clean out is going to get whatever it was before, which means we're just going to assign it itself. So for last, I saved the most difficult component, which is the FSM counter. And the FSM counter, as you remember, is the logic that's taking the clean output of the debounce hardware, and on every rising edge, it's going to increment the counter here and load that count into this register to be displayed on the LEDs. So what makes this module somewhat difficult to implement is that it requires kind of a different technique than just a simple combination of statements. It takes something like a flowchart to properly implement the functionality of this. So for instance, we want this module to be in a state where the button isn't pressed, and it just transitions to another state when the button is pressed, and it monitors these states to properly implement our logic that we need. So usually it's a good idea to implement a finite state machine when you have a bit of more complex logic, where you want to implement kind of a flow chart type of logic in VHDL. So probably the best way to get started on developing a finite state machine is to first define the states that are going to be involved in this machine. For right now, let's forget about VHDL and think about what do we want this finite state machine to do logically. Well, first we're going to need some kind of state that's a sort of default safe state to be in, and I'm just going to call this the initial state. After we enter this initial state, we want to transition to checking whether or not the button is being pressed or not. So for the next state, I'm just going to assume button not pressed. So this will be the button not pressed state. We are going to go from here to here. Now, if the button does become pressed, what we want to do is transition from a button not pressed to a button pressed. So if clean in, because remember the input to our finite state machine is the clean in input, if that is equal to 0, which means the button is pressed, then transition to button pressed. So we'll go from initial state, so even if the button is pressed before it goes into the state, it will check this condition and immediately transition over here. And then when clean in goes back high, what we want to do is we want to just go back. So this is kind of what it's beginning to shape up to look like. But there's just one more thing that we're not accounting for in these two states that our finite state machine needs to accomplish. When the button goes from high to low, which means the button gets pressed, what we want to do is we want to increment this counter and load the register. And we don't have that implemented in our logic yet. You could say you want to increment here, but what we're going to be doing is we're going to be iterating over this pressed state over and over and over again until it's not pressed. So if you were to kind of do something like that, then unfortunately what would happen is that the counter would just keep incrementing until you are not pressed. So what you need to do is you need to create another state that goes in between the transition from not being pressed to being pressed. So I'm going to put the next state here, and I'll eliminate that connection. So now I have the increment counter state. When clean input goes low, we will go to increment counter. And then I'm going to add another state for loading the register. And with this new state load register, we're going to go immediately from increment counter to loading the register. It will go immediately from this state to this state. Whereas in these two states, there could be multiple iterations where we just keep returning back to the same state. In the case where button is pressed, we're going to keep returning back here until the button is not pressed anymore. And here, we're going to keep iterating in this same state until the button suddenly becomes pressed, and then it will go through these two states. And then after load register, it's going to go straight into here. So hopefully this makes sense. We have our default reset state, which will immediately transition to button not pressed. If the button does become pressed, which is checked by this condition here, it's going to go immediately to increment counter. Then the very next step will go to loading the register, and then it will go immediately to the button pressed state, and it will keep iterating into this state until this condition is satisfied, where the clean input goes high again, which means the button is no longer pressed. Then it will return back here, and it'll just simply wait for the next button press. So now that we have this defined, it'll make programming the VHDL much easier. So let's just go ahead and add the FSM counter. Right click, new source, VHDL module FSM counter. Our inputs are the clean button, the clock, reset, and for outputs, we have the counter out, which is also a bus that goes 3 down to 0, and then we have the load register signal. So to implement the flowchart that we defined earlier, what we're going to do is that we're going to declare a new type. And the concept of a type is similar to a lot of different programming languages. Here I'm going to write type, state type is state init, state button not pressed, state increment counter, state load reg, state button pressed. So you probably recognize that the names in here are the names of the states that we are using. We declared a type called state type, and what we're going to do is we're going to create an instance of that type. So signal state is of type state type, and it's going to get initialized at state init. And then I'll just do the normal thing where I make signals for my outputs. And for our process, the process I'll call FSM count, process clock, and reset. Again, if the reset is high, then so at reset, we want the state to get initialized back at the initial state, else if on the rising clock edge. Now, everything you saw so far is pretty straightforward, and it kind of looks exactly like the modules that we created last time, except for this new type that we defined up here. But here's kind of where the differences will be in this next block of code that I write. Here I'm going to make a case statement, where case state is, and then I'm going to create a condition for each of the possible states that this state could be assigned to. So now that I have this kind of block constructed, what I'm going to do is I'm going to create the logic that I want to be carried out in each of these states. So for instance, when the FSM counter is in the increment counter state, what I want to do is I want to increment the signal S counter out. And I'm just going to write logic for each of these. So for the initial state, it's nothing fancy. It's just pretty much going to be exactly like the reset, where we just zero out the signals. But after the initial state is carried out, what we want to do is we want to assign the state to the next state, which is going to be button not pressed. If you remember here, after our initial state, we're moving directly to button not pressed. So that's what this is going to do here. We want to assign the state button not pressed. Now in the button not pressed state, it's going to be where we check the condition whether or not the clean button input is high or not. So if the clean button is equal to 0, which means the button would be pressed, then we want to transition to the state increment counter, else we want to just remain in this state. So that's all this is doing, is that it checks to see if the button is high or not, and if it is, well, if it's pressed, then we want to move on to the next state. If not, then we're just going to keep assigning state itself. We're going to keep returning to this logic until the button goes low, and then it's just going to move through the rest of the states. So in the next state, the increment counter, all it's going to do is take S counter out and add 1 to it, and then move on to the next state. To load the register is also pretty easy. All we're going to do is just assign the sLoadReg signal high, so that way the external register will load the signal that is on counter out. And then finally we move to the button press state. And in the button press state, we're just going to remain in button pressed and wait here until the button goes high again, in which case that means the button would be not pressed anymore. We don't want to go directly back to button not pressed, because then it's going to see that clean out is still 0 and it's just going to keep counting until you release the button again. So that's why we need this state to wait until the button is no longer pressed. So when button pressed, if clean button is high, which means it's been released, then the state will move on to state button not pressed. Else states will stay the same. Will remain in the button press state. And that's it for the FSM counter. All we have to do is add the IEEE library, so that way we can do the arithmetic. And I think we're done. Oh, syntax error near load reg. Oh. Okay, yep, we're done with that one. And now we can see here that we have all 4 VHDL modules defined in our project, and they're the 4 modules that we need right here. But unfortunately, there's still one more VHDL module to create, which, is not depicted here, but arguably the most important one that we need. It's called the top level. And in the top level, what we have to do is we have to create pretty much a single module that envelops all four that we created. So this is important to do because not only does it help us interface to our peripherals, but it also will declare the connections that are made. Because if you paid attention closely, you would have saw that nowhere in our VHDL code did we declare that this clock input, for instance, was going to connect to the onboard clock, or that the clean out of the debounce hardware is going to connect to the FSM counter. So in order to interconnect multiple VHDL modules, it's incredibly necessary to create this top-level design to encapsulate everything. Now to do that, we're just going to start with new source and VHDL module as usual. In this case, I'm going to call it the counter top level. And it's going to have the clock input, the button for reset, the button for incrementing the counter, and finally, I'm just going to call the outputs the I/O for the Mercury Board I/O. And that's going to connect to our LEDs. Now creating the top level can be a little tricky at first, but once you get used to creating the top level, it will get to the point where this portion of your project is the most tedious portion. And this is also kind of where creating your map really comes in handy. So what you're going to do first is within this architecture line, so you're going to declare the debounce hardware, the clock divider, the FSM counter, and the register. You're going to declare all those there. You're also going to declare the signals that interconnect those modules, and finally the signal that precedes the output. So to declare a component, what you want to do is you want to click on the module that you want to declare, and then double click this guy to run it. Yes, and what it's going to do is it's going to create kind of this sort of block code that you're just intended to kind of copy and paste. And this little block right here is your declaration. Copy that guy and just simply paste him in. And then you can simply use the same method for the rest of the modules. So now that you have all of the modules that you want in your top level, what you want to do is you probably notice that register LEDs has this sort of weird icon next to it. Well, that icon actually denotes which one of your modules is the top level. So of course you want to make this one your top level, so you just right click and say set as top module. So we got everything declared, and now the next thing is to make the connections in between the modules that we want. So it's the same thing that you saw before. By opening this up, you also get this block of code. So if you copy and paste that, that is intended to go beneath this begin statement. Kind of where your processes would usually go, but here what you're doing is you're creating an instance of the debounce hardware. So it's debounce hardware like instance basically. This name is purely arbitrary. The debounce hardware port map, and so you're just assigning the inputs and the outputs to signals. And by assigning inputs and outputs to similar signals to other VHDL modules, that is how you're connecting the modules together. However, for external peripherals like the clock, megahertz, the onboard button, and the external button, you can directly connect those to your inputs of your VHDL modules inside. So for raw in, you can connect that directly to button increment counter, the incrementing button up here. Now the clock, we want the clock slow that gets outputted out here, so I'm just going to create a signal for the slow clock. And to save time, I'm just going to declare all the signals ahead of time here. So I made display LEDs as a signal that's going to precede my I/O LED output, so I'm just going to put that down here, kind of the same way that we do for VHDL modules. Now the clock for the debounce hardware, I want to assign that to the slow clock that's coming out of the clock divider, and so I made this S clock slow for that. So S clock slow. And the reset, since reset connects to an external input, that's just going to connect directly to button reset. Clean out will connect to the S clean button, which the signal S clean button will connect to this input of the FSM counter. So now I'm just going to throw in the port mappings of the rest of the modules. And here I'm going to write the signals to the rest of these inputs and outputs for these VHDL modules. The clock of the clock divider connects just to the onboard clock. So that's just going to get assigned clock from up here. And you're not going to get an error because the input of the clock divider shares the same name with the input of the top design. Xilinx is going to know what you're talking about when you're assigning the clock of the input of the clock divider to the clock input to the top level design. In clock slow, we want to connect it to the clock of the debounce hardware, so that's going to get assigned to clock slow. Now the FSM counter, that connects to the clean button input here, connects to the clean output of the debounce hardware. And I assigned that to S clean button, so that goes to S clean button. Clock is the same way, goes to clock. Reset is the same thing too, it goes to button reset. Then for counter out, I'm going to give that to S count, which is also a 4-bit signal. And low drag, I'm going to hand that off to the signal S low drag. Now for the register, clock goes to clock, reset goes to button, reset. The counter in of the register connects to the counter out of the FSM counter. So that connects to S count. Then load register in connects to load reg, the load reg output of the FSM counter. So that's going to also go to load reg. Then display LEDs is going to get assigned to the signal S display LEDs, which that's going to eventually go out to the input and output pins on the Mercury board. You can see it here, display LEDs, that's going to get outputted to the LEDs. So that goes to signal display LEDs. Then if you save it, it kind of creates a tree for the top level. That within this top level is consisted of all these several different VHDL modules. And you can actually see the circuit of how all these are connected, and this is kind of a neat little debugging tool, is that if you select the top level, synthesize view RTL schematic. So here, what we're going to do is we're going to select the instance names of our VHDL modules and add those to the selected elements that we want to use to create our schematic. So here you can see this shows you how the VHDL modules are interconnected to themselves in your FPGA. You have the clock divider here that takes in the clock external input. That's the 50 megahertz clock. The play symbol denotes the output because the clock signal is coming into the FPGA out from the clock, and it stops at the clock divider and the FSM counter and the register. You can see that these are connected, that the FSM has the output load register that connects to the load reg in, and that the display LEDs are connected to the I/O output. The button increment goes into the debounce hardware. The button reset connects to these 3 modules. So using this RTL schematic, you can kind of see and make sure that your top level is wired up correctly. So that's just kind of a cool thing to look at and just kind of a neat little tool. And then just one last thing, we just want to make sure that we add our Mercury UCF file. The Mercury UCF file is something I went over in the previous video. And in the previous video, I showed you where to get it. So here I'm just going to quickly add that. So I have the Mercury file here, and opening it up, you can see I don't have inputs and outputs called button reset and button increment. And just simply what I've been doing to interface to the inputs and outputs for a specific input or output is I've just been renaming pins in the Mercury UCF file. For clock and I/O, that's actually already in here. I/O is going to be these four guys. So what I'm going to do is for I/O4, I'm just going to name this one button reset and button increment. That should be all I need to do, and then obviously the clock uses that guy, so you don't need to change that. Save that. And now I'm just going to generate the programming file. What error? Oh, yep. Got burned again by this. Make sure that you have allow unmatched LOC constraints. Alright, so we look all good here, and we're almost done. It's now just a matter of building the circuit and uploading this design to the Mercury FPGA board. So now we'll just start up the Mercury programmer to upload the bit file to our FPGA board. Just click connect and then browse for that bit file. In your documents, you probably have the Xilinx folder, and I'll just go to binary counter, and right here the counter top level bit, and yep, just burn that to the board. And now I'll show you on the circuit side. As you can see, the VHDL is currently running at the moment. I would have showed you how to build the circuit, but connecting LEDs and setting up a button with a pull-up resistor is pretty easy, so just kind of thought I would leave that up to you. This button, when it's pressed, it has this pull-up resistor here, and when it's pressed, it will pull the node down to ground, which is this green wire, which is connected to pin 6 on the Mercury board, and these LEDs are connected to the 4 inputs and outputs on the Mercury board as well. And then I just have some wires that connect from the 3.3 volt node here, and then just the ground pin from the FPGA connected to the rails here and here. And if you press the button, you can see it counts in binary on the LEDs, and it will just kind of loop back around once you reach hex F. So here it will count back down to 0. And at any count you want, like 4, you can just simply reset all the VHDL modules inside of the FPGA just by simply pushing the button. So from 6, and then set it back down to 1, 2, 3, 4, 5. So, well, I hope this video is really useful for you, and thank you for watching.